1.
Okay, welcome to your guided notes video style for 8.6, which is about exponential decay instead of growth. So the first thing, let's write down the definition here. It's a quantity for decay that decreases by the same percent over time. So the main difference in your usual format from last section was a times b to the x. Remember, a was your y-intercept. The difference now is that b will, for decay, will be less than 0, but it'll also be so it'll be less than 0 and greater than 1. So basically your b value will be something like 1/2 or 1/4 or 0.75. Okay, so if we look at the first example, the first thing we want to do is graph the function of 1/3 x. Again, this is decay because the b value, your growth factor, is less than 1. So first thing we're going to do is make a table. So with this part, the domain or your x values is all real numbers. And when you plug in, obviously we start at the y-intercept. The y-intercept is assumed 1. And then 1/3 to the 1 is 1/3. 1/3 to the 2 is 1/9. Now 1/3 to the -1 is going to flip it over, so that would go here. This would make it 3/1, or just 3, and here to the -2 would be 1 to the -2 and 3 to the -2 switches position, so this would be 9/1, which would just be 9. So then step 2 is to plot the points. So we'll start at the y-intercept at 1, and then 1 1/3, 2 1/9 is almost right at the x-axis but never touches, and then -1 3. And then for -2 we go up to 9. All right, now we're going to draw our smooth curve. That is your first example of a graph that has exponential decay with our smooth curve. From either table or the graph, you can see that the range is all positive reals. So that is example 1. In example 2, we're going to graph another one, but our a value has changed. So we're going to compare it to 1/3 to the x. So I can just replace my numbers from the first table here. So I will just say this is 9, 3, 1, 1/3. These are all the numbers from example 1. And then here, our new y-intercept is going to be at 2. And then this is going to be a little different. So this will be 2/3, 2/9. And over here, this will be 6 and 18. So now when I graph this function, you'll see that we go -2. We'll start at the y-intercept, so that will be 0, 2. And then we have -1, 6, 6, -1, -2, 18. That goes hold on here. So -1, 6 is here. Negative 2, 18 goes off the graph. 0, 2 is here. 1 2/3 is here. And then 1 2 2/9 is here. I draw my smooth curve. It looks like that. Then for my other one, which is the 1/3 to the x, I have 0, 1, 1, 1/3, then the really small one, and then negative 1, 3, and then negative 2, 9. So it looks like very, very similar like that. So with that being said, you can then make the statement, because the values of y for y equals 2 to the 1/3 x are 2 times this corresponding y values, the graph is a vertical stretch. So you can see again, if I compare it, this is the original, and then here it's same thing, but it's just vertically stretched a little longer. So I'm going to pause the video here and have you try checkpoint number 1. All right. Example 3. We're going to tell whether the graph represents growth or decay, and then we're going to write the rule. So by looking at this, could you tell me if this is growth or decay? Of course, it's definitely decay. So the y-intercept here is going to be at 5. So that's my y-intercept. So that means my a value is going to be 5. Then I'm going to find the values of b by using 1, 1. So I'm going to still have a equal to 5. But now I'm going to plug in 1, 1. So I'm going to put 1 for for y. A is 5. And then b to the 1. So that gives me b equal to, let's see here, 0.2. So the function rule would be y equals 5, 0.2 to the x. Because again, here you divide each side by 5, and 1/5 is 0.2. This is a nice model here. Again, the growth, it grows, your b value is larger than 1, and here it decays, your b value is less than 1 but bigger than 0. So it looks like that. The last part of this section talks about exponential decay model. So instead of compound interest that gets bigger and bigger your money, you'll get smaller and smaller exponentially. So not much has changed. This is still your amount for A. Your R is still your decay rate now. So it's your rate still. T is time. But now instead of 1 plus R, you're going to do 1 minus R. That's your decay factor. So really, you're going to be using y equals A times 1 minus R to the time. So here's an example, and then we'll have you do the last couple checkpoints. So if you read this example carefully, you'll see that it was population in a city decreasing, so that's the decay model, from 95 to 2003 by 1.5%. And then there was initially 357,000 people. It says write a function that models the city's. Yeah, we're going to stop in 30 seconds. So I'm going to pause this video. I'm running out of time, unfortunately. We'll finish this together, and then we will have you do the checkpoint. And that makes me very happy.